Here's my tutorial for pennies in a circle off the Desmos graph that we did in physics. As the radius of a circle increases, how would the area change? We know that the area changes with the square of the radius of a circle. And this is not the full answer. I am not going to write down all the answers and all the things for all time, because I do expect that you can pay a little attention. But remember, the area of a circle is pi r squared. That's the area of the circle. That is not the full answer for a quiz. That will not be all the points. It's that the area will change with the square of the radius. As the area of the circle increases, how would the number of pennies fitting in the circle change? Now, as the area increases, the number of pennies will go up in a linear fashion, by which I mean if the area doubles, the number of pennies fitting in will double. If the area triples, the number of pennies fitting in will triple. So it varies directly would be a great phrase, that it varies directly. If the area doubles, the number of pennies doubles. It varies directly. When the graph uses d squared, what is that standing in for? Well, that's basically standing in for the area of the circle. What's the real formula for that? Pi r squared, of course. Now, I want to make the point that I have proven over and over again that it's almost impossible to memorize your way through these things. You need to understand it and review. Okay, and I can answer questions, I can meet you for tutoring, but I'm really recommending that you actually review this and make it yourself understand it. What multiplier needs to be used to get d squared to actually be the area of a circle, and why? Okay, because d squared, and you need to write, and y. Kids keep forgetting y. So we'll address that. D squared is not the area of a circle, is it? And the number of pennies is standing in for area of a circle. What they wrote was n equals ad squared. And I'm pointing out that the number of pennies is essentially the area taken up in a circle. And I could make the number of pennies be stand in for the area of a circle. When we put in the number of pennies, we get, of course, a bunch of circles like this. And my point is, if we melted these down, we could make this be a circle of an appropriate size. If I melted down 4 pennies, I could melt them down and pour the metal in at the same average thickness, and I would get a circle that is the same size as 4 pennies. It's just that it would be one circle without any little gaps. So the number of pennies is a stand-in for the area of the circle that these would create if I could do that. So let's say that the number of pennies is essentially the area of its own circle, and that's equal to this. But what is the diameter? The diameter is 2 radii. So this turns into that, and area of a circle is pi r squared. So this is the area of a circle, and this is the area of a different circle. But this isn't mathematically the area of a circle, is it? Not mathematically, because this is going to turn into 4r squared, isn't it? And 4r squared is not the area of a circle. This alone is not the area of a circle. What adjustment factor needs to be made to turn this into the area of a circle? Well, it's missing pi, so let's multiply by pi. And 4 is not in the formula for area of a circle, so let's divide by 4. So this adjustment factor times that turns it into the formula for an area of a circle. And now I have effectively the area of a circle. This is not the final answer for A. It's just turning this into the area of a circle, because d squared is not the area of a circle. Having said that, what they actually talked about was that the area of the pennies on the left, that remember the number of pennies was essentially the area of the pennies. And then this was essentially, now it is the area of a circle. What's the relationship to that? We know that the area of the pennies will not be the whole circle area, will it? Is it half? Is it 25%? Is it 89%? What fraction of the whole circle will the pennies fill with their own area? Because there are all the gaps. So we know it's not 100%. The area of the pennies will not be the total area of the circle. So let's take the area of the pennies total divided by the area of the circle that they fit in, and that would be the percentage, effectively, wouldn't it? We're not going to use a percent exactly, we're going to use the decimal number, but it's pretty much the same thing. So which circle would we use? Number 7, to calculate the proportion, which this is a proportion, of the area of the pennies taken up in a circle, what data would you use? The biggest circle or the smallest, and why? I would use the biggest circle because it will have the least percent error, I assume. If you have a big circle, just mentally draw a giant circle. And I mean one that like you'd have to walk across, and then you fill it with pennies. Pretend you're off by 1 penny. That's not much percent error, is it? If you have a circle just this big and you fill it with pennies and you're off by 1 penny, your percentage that you were off by is much higher. So the bigger the circle gets, presumably the less percent error we have. So that's why I'm going to choose the biggest circle. Number 8, do you know another use of data to find good numbers to use for this? Put another one. Now the other version would be, if you're taking the same kind of data over and over and over, you want to think of something else. Now my example was, we put a kid on the roof of the gym and have him drop a ball off, and we time with a stopwatch the time it takes to hit the ground. We do it over and over and over and over and over again. We get a time. Now, here's my graph of my pretend experiment, trial 1, 2, 3, 4, and on and on and on. And so I got this time and that time and this time and that time and this time and that time, this time, and so forth. And they were all pretty close. And then let's pretend I got this one up here. And then I got another one, another one, another one. And I got this one down here. And another one. I got this one up here. Since I was doing the same kind of experiment over and over, what are the chances that these two high ones, extra high ones, and this extra low one are correct? Basically 0. There's no way that's right. If these are right, how come they're I only got those once in a great while, right? If they were correct, they should be the kind of thing I got a lot, right? I think these 3 are screw ups. So what I mean in number 8 is, another way to treat the data is to throw out the outliers and average the rest. Now, some people will point out that their teacher said just throw out the high and the low. Okay, if your data was doing a graph like this and they were all pretty much the same, yeah, then maybe just find the high one and the low one and throw out those. But if you have multiple outliers where it just seems like there's no way that that's right, like here I showed 3, let's throw out the outliers and average the rest of them. And that's what I mean for number 8. So on number 9 and 10, we try both methods. Here is the data for number 5, and I used 37 pennies times the area of 1 penny. This is the radius in inches for a penny. So pi r squared is the area for 1 penny, and I fit 37 of them in the circle. And here is the radius in inches for the circle, and pi r squared is the area of the circle. You'll notice that the pi's cancel out, so let's just skip that. And we end up, grab a calculator, see if you can do it, we end up with 0.77 is the adjustment factor between the area total for pennies and the area of the circle that you can shove them into. The pennies will occupy apparently 0.77 or 77% of the area of the circle that you can cram them into. So that's choosing the biggest circle method. Let's try the other one. And here I did the same thing for all my 4 other data points. And like I said, one way to do it would be to throw out the high, this is the high, and this is the low, and average the other 3. So I took the average of the other 3, and I got this. Well, all these data points aren't equal, are they? Because I didn't do the same thing over and over. I kept using a bigger and bigger circle, which means my percent error is probably going down, 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 down. And by that logic, number 5 is probably my best bet. Also, look at the values we got for the adjustment factor that I'm calling K. It got bigger and bigger and bigger and bigger. And it seems to be approaching some number, right? In fact, it's getting bigger by a smaller amount as we go through, it seems. So this is approaching some number, and maybe if we did it with an even bigger circle, maybe we get 0.785 or something. But that number is not too bad. I assume my percent error is not too bad in that one. And so which is more logical in this case, in our case, that we really did, to take the average of the middle or just take the biggest one? Well, since it seems like the number goes up every time I do another version where I think the percent error is lower, let's just take the biggest one as my best number. Let's not use the average at this time. Again, the average is meant the average of the middle ones, or the throwing out the outliers and averaging the rest, are meant for times when you did the same kind of data collection over and over and over. And that's not what happened because I kept using a bigger and bigger circle. How well do these two values match? Why do you think they match as well or as poorly as they do? Well, they match not so bad. It's only 4.3% different between these and those. But that's probably because there's really not much human error in the data. You know, it's not hard to drag those virtual pennies into that virtual circle. And you can just practice and jam them in and move things around until you get a good piece of data. So there's not really much human error in there at all. And this number isn't all that much different than that, really. It's only 4.3% different using our percent error math here. But still, I would pick this number instead of that one. What might be improved in the gathering of the data? Well, sometimes the final, penny here, sometimes the final penny wouldn't stay in the circle, so I could just count it anyway. And I think what happened, in fact, when I got 37 pennies was that visually I could see that 38 would fit, but it wouldn't allow it. I know that happened at least at one point. So I could just mentally go ahead and say, well, I'm going to add that one in because it should be in there. So sometimes you know better than the apparatus, or you know you started late or with the timing or something, and you can just throw that one out. Or sometimes, of course, your machinery needs to be recalibrated or tested or something. In this case, I think we could just try to account for the computer error of not allowing a penny in that really should be in there. Which K value do you trust more and why? I trust the number 5 because the values keep approaching the number 5. They keep going up. And well, I said at a pretty steady rate. I think it's maybe actually decreasing, but anyway, they keep going up. So what's more likely, that the bottom one is right? No, because they keep going up. And or that the middle ones are right? No, probably not even that, because they keep going up. So this is probably the closest to the true value that I have. And maybe it's supposed to be, again, like 0.785 or something, but this is the closest one I have in my available data. So that's the one I'm going to pick. And human error is pretty low. Yeah. So I don't think that I need to adjust much for my human error, because in this case, there really wasn't much at all. Take the more trusted value for what we will call K for a constant and put it into an equation that has the area of the pennies on one side and the area of the circle on the other. Okay, remember that we said d squared isn't in the area of a circle until I multiply it by pi over 4. So here's the area of the circle with my adjustment factor. And here's the area of the total pennies, which is the area of 1 penny times the number of pennies. But they're not equal until I multiply by my adjustment factor, because the area of the pennies total is not the area of the circle, is it? We said it's 77% or 0.77 of it. So these aren't equal until I multiply by my 0.77 number, and I bring this value total down to 0.77 of what it was before. And then it is the total area of the pennies. So rearrange that equation so it's essentially what Desmos had, because Desmos had it as number of pennies equals adjustment factor A times d squared. So let's get n by itself. And how do I do that out of here? I divide by area of pennies, and that comes under here. Now I want what all my other stuff times d squared. And I know some kids will write d squared in the numerator. But my point is I want d squared off by itself the way that they had it here. And I want everything else to stand in for A. So this is the stuff that stands in for A the way they had it, capital A. And I wish they wouldn't use A because it tends to stand for area so many times in geometry and math class, but that's what they had. So their adjustment factor, capital A here, we have decided is really hiding all of this. Well, I know what those are. I know the area of 1 penny. I know what K is, and I sure know what pi and 4 are. So this is not a mystery. We can boil this down into one number. Let's take the value for K and pi over 4, and let's find out what it is. However, I do need to make one little more statement. The area of a penny, then, isn't it pi radius of a penny squared? And then this talks about, here's the radius of the penny, and we need to use centimeters because when they wrote the graph, they used diameter in centimeters. So this isn't going to work unless I use radius of a penny in centimeters. So I'm going to use radius of a penny squared times pi is area of a penny on the bottom. This remains the same, times d squared, because that's the way I want to set it up. And here's the number of pennies. So use the value of k in the penny radius to find the value of a. Now notice back here that the pi's cancel out, so we can just ignore them. So let's just take k over 4 divided by the radius of a penny squared. And it turns out we get 2.12. Does it agree with the experimental data closely? Well, yes, it does. And when we did it for real on the graph, on the computer, we got, well, some people claimed it was 0.21, and some people said it was 0.22. So this is a pretty darn good value, which proves that our math must have been right, because otherwise, how did we get it? I mean, we got something that agrees with a real life experiment. And so that proves our logic must have worked. Our math must have worked. If our calculation didn't agree with the experiment, which one is the first one to be suspect? Why? Now, this is what I actually worked out. When I got help and we got confused, we immediately suspected our calculation, because with that computerized experiment, we were very confident of the data. You know, it was counting the pennies for us, and our human error was extremely low. So instead of saying, oh, we must have messed up the experiment, in this case, we said, oh, we must have messed up the calculation. So which is the first to be suspect and why? Our calculation is the first one, because the data doesn't involve much human error. If the experimental data is suspect, what could be done about it? Well, you could go and perform it again. It could be performed again, and we could just mentally put in the number of pennies we think is correct. Remember that I said maybe if the number is really bad, maybe you just go back and do it again. And if you think it should cram in 2 more pennies and that the computer is kind of cheating you out of 2 pennies, then just mark down 2 more pennies in your data table and use that. And maybe our 37 turns into a 39. What is suspect about the last data point from most experiments? The point here is that the data at the end of an experiment is sometimes the end point of what the machine's ability is to measure. It's usually at the end of the machine's ability to measure, so it's often the least reliable data point. So in a different kind of experiment where the machine is doing all the measuring and so forth, if it's right at the end of the ability to measure, then maybe the machine is unreliable at that point, and maybe that should be considered an outlier, and we shouldn't rely too much on that data point.